and the statistical physics of indistinguishable particles. We talked earlier about photons, which are bosons, but now we're particularly interested in bosons or fermions, for which there's a conserved particle number, for which particles can't be individually created or destroyed, and then there's a chemical potential that governs the free energy as a function of the number of particles. And so we can define a distribution function of energy, which is the expected number of particles in an orbital, which has energy E if the temperature is tau and the chemical potential is mu. And we saw by computing the Gibbs sum and the expectation value of the number of particles that we can write that as 1 over e to the energy minus chemical potential divided by tau plus or minus 1, where the plus or minus, well, the plus is for what? For fermions. The minus for bosons. Oh, a very important plus or minus sign. So these are called the Fermi-Dirac in the case of fermions, and Bose-Einstein in the case of boson distribution functions. In the case of Fermi-Dirac, if this is the chemical potential, when the energy is equal to the chemical potential, the expectation value of the number of particles in the orbital is 1/2. And so we get a curve that looks kind of like that. They're fermions, so there can't be more than one particle in each orbital. When the energy is small compared to the chemical potential, the occupation number is very close to 1. When it's large compared to the chemical potential, it's close to 0. The Bose-Einstein distribution actually blows up as the energy approaches the chemical potential, so it looks something like that. That's Bose-Einstein. Down here, they nearly match, where the value of f of e is small compared to 1. That's the case in which, in the denominator, the exponential is much larger than the plus or minus 1, so the plus and minus 1 doesn't matter very much. We call that the classical regime. The difference between bosons and fermions, well, it's not a very important distinction when the expected number of particles in each orbital is very small, because double occupancy is really rare, and the Pauli exclusion principle doesn't make much difference. So the classical limit is the one in which we can ignore the plus or minus 1. Then the distribution function is just e to the mu minus energy divided by tau, which is small compared to 1. And sometimes we write that as lambda e to the minus epsilon over tau, where lambda is the activity e to the mu over tau. In the Bose-Einstein case, the chemical potential will actually have to be less than the energy of the ground orbital, the lowest energy orbital. So we're always on the right-hand side of where this curve runs off to infinity. Then we talked a little bit about classical gases, and in particular, the isothermal or isentropic expansion and compression of a classical ideal gas. I'm stepping on chalk. The reversible expansion or compression of classical ideal gas. Reversible means we do it very slowly. The system stays in its most probable configuration during the change. We noted the first law of thermodynamics, which is just conservation of energy, says the change in the internal energy of the system can be written as tau d sigma, where sigma is the entropy, minus p dv. Or in other words, as the difference between the flow into the system and the work done by the system, the flow of heat into the system. This is heat added to system which increases the internal energy. This is dW, means work done by system, which is done at the expense of internal energy. In the isothermal case, what happens to the internal energy if there's an isothermal change for an ideal gas? What happens to the internal energy? It doesn't change, because the internal energy for an ideal gas, a monatomic ideal gas, is just 3/2 n tau. So isothermal, same temperature, we're keeping the number of particles fixed. That means du is 0. And since du is dq minus dw, it means that dq is equal to dw. So the work that I do when I compress the gas, well, if the gas expands, it does some work. Where does the energy come from to do the work? It comes from the reservoir, which is maintaining the system at a constant temperature. There's a flow of heat into the system, and that allows the expanding gas to do work. If I want to reverse that, then I can compress the gas. I'm doing work on the system in that case. The internal energy isn't changing because it's done isothermally. That means the work that I do produces a flow of heat from the system back to the reservoir. And in the isentropic case, isentropic means the system is insulated. It's isolated from any reservoir. So in that case, what's the heat flow? It's 0. There's no flow of heat. That means the change in the internal energy is just equal to minus the work done by the system. Therefore, if the gas expands doing work on the system, what happens to the gas? It cools. It has to lose internal energy. That means that its temperature decreases. And if I then reverse that isentropic expansion with the system still isolated from any reservoir, now I'm doing work on the gas. And what does that do to it? Right. The work increases the internal energy. That means the temperature increases again. And if everything's done reversibly, it comes back to its original configuration when I reach the initial value of the volume at the original temperature. And everything is, I've undone the effect of the expansion using the reversible compression. One thing we didn't have time to talk about last time is the case of free expansion. So now I imagine that I've got a box, and it's divided into 2 halves. There's a valve. It's got a plug in it and a hole separating the 2 boxes. I initially have gas on the left side. I open the valve, and then the gas flows through the hole to fill the other chamber. That's what I mean by free expansion. And it happens rapidly. We can imagine the system is insulated during the free expansion, so there's no heat flow. But actually, even if it weren't isolated from the reservoir. Because the expansion is so rapid, there's very little time for heat to flow during the free expansion. So there's essentially no heat flow during that process. And then the system rapidly re-equilibrates and comes to its new most probable configuration, filling the larger volume. So in that case, how much work is done? How much work is done by the gas during the free expansion? Doesn't do any work, just freely expanding into the other chamber. So that's equal to 0. How much heat flow is there? Well, I just told you. There's no heat flow. And what happens to the internal energy, therefore? No work done, no heat flow, therefore internal energy doesn't change. So the volume increases from the initial volume to the final volume, but the temperature, what's the temperature compared to the initial temperature? If it's an ideal gas, it's the same. Same internal energy, same temperature. Okay? Of course, once it comes to its new, most probable configuration, we can calculate what the new entropy is. Remember the formula for the entropy of an ideal gas. What is it? It's N times what? All right, I think I heard all the right words. It's the log of quantum concentration divided by concentration plus 5 halves. Now, if I remember the quantum concentration goes like temperature to the 3 halves, I can write that as N times log tau to the 3 halves volume divided by number of particles plus a constant. We change the volume. Now the volume is larger than before after the free expansion. So the final entropy minus the initial entropy, the number of particles is the same, temperature is the same, but volume changes. So it's N times the log of the ratio. It's the difference of log V final and log V initial. I guess I'm trying to remember to call it Ln, so you know it's a natural log. And so it's N times the log of the ratio of final volume to initial volume. Well, that makes sense. The entropy is counting the number of accessible states of the system. Now, the same number of gas molecules are in a larger volume, so there are more possible states that the system can occupy. So the entropy increases. There are more accessible states. But now, I made a mistake. I didn't really want the gas to fill a larger volume, so I want to return the volume to its initial value. Well, I know how to do that. I can compress the gas. I push in the piston, say, returning from the volume that it expanded to the initial volume. Let's say I do it isothermally. In contact with the reservoir at temperature tau, returning to the initial volume, so, well, what I'm calling V final during the isothermal compression is really the initial volume. But anyway, I return the volume of the big box to the smaller volume of the little box. And what happens to the temperature? It's Well, it's isothermal, right? So the temperature never changed. When it freely expanded, the temperature was the same as initially. Now I've compressed again, keeping the temperature the same to the initial volume. So it looks like everything's just the way it was. I put the volume back to the initial volume. The temperature is the same as before. The internal energy is the same as before. Has anything changed in the world? Sorry? I did work, right. And where did that work go? It went into the reservoir. So this process, which returned the gas to exactly the way it looked initially, isn't really completely reversed. There's been some change. The change is that there was flow of heat to the reservoir during the isothermal compression. So although the entropy of the system is unchanged, because we're back in the same configuration as initially, the change in the entropy of the reservoir is positive. The entropy of the reservoir is increased. So the whole universe has higher entropy than it did initially. Well, that's the hallmark of an irreversible process. Something happened that we can't undo. The system looks the same, but the total entropy of the universe is increased. The entropy of the reservoir has gone up. I could have instead tried to recompress the gas isentropically. Question?
Does the heat flow from the system to the reservoir?
It does.
But then how come the entropy is unchanged? Shouldn't it be less?
The entropy of the system, you mean?
Yeah.
Well, the entropy of the system did decrease during the compression. So what I'm comparing is the change in the entropy starting from when starting from when the gas had the small volume. Then we let it freely expand. That increased the entropy of the system, but I undid that increase by isothermally compressing the system. Okay, and the entropy of the system during the isothermal compression, which is a reversible process, went to the reservoir. But if I look at the whole story, I started out with the gas in volume V initial. I let it freely expand. Then I isothermally compressed it. The entropy has increased in the full process. The increase really occurred during the free expansion. But then I tried to undo it, but I couldn't completely undo it. I can undo what happened to the system, but only at the cost of increasing the entropy of the reservoir. If, on the other hand, I had isentropically compressed, back down to the initial volume, so then what would happen to the entropy of the reservoir? Nothing, because it's completely isolated from the system, right? So in that case, the change in the entropy of the reservoir would be 0. But what happens during the isentropic compression to the entropy of the system? Isentropic. Stays the same, right? So during well, you were anticipating, I think, the next thing I was going to ask. During the compression alone, no change in the entropy, but during the free expansion, there was a change. The entropy of the system went up. So after I isentropically compress, I'm back to the initial volume, but with larger entropy. And what about the temperature? I've heated up the gas because no change in the temperature during the free expansion, but when I compressed it isentropically, I increased its internal energy, right? There was no heat flow, but there was work being done. The internal energy went up, its temperature went up. So although nothing happened to the reservoir in this case, I haven't returned the system to the initial configuration. It's in a configuration with the same volume, but with higher entropy. Either way, the total entropy of system plus reservoir, in this case, then entropy of system overall increases. Either way, entropy of system plus reservoir increases. that's an irreversible process. Okay. So now, enough classical. Let's talk about an ideal gas in the quantum regime. A quantum ideal gas. So instead of just talking about the tail of the distribution function, where it's very small and the difference between bosons and fermions doesn't matter, let's get away from the tail. Well, I'll write the distribution function again, though it's still on the board. We'll be seeing this a lot. 1 over e to the energy minus chemical potential over tau plus or minus 1. Plus for fermions and minus for bosons. Now, if the Fermi gas is at strictly zero temperature, suppose it's Fermi-Dirac, talking about fermions at zero temperature, then the distribution function makes an abrupt change right at the chemical potential. It makes a step like that. At strictly zero temperature, we call the chemical potential at zero temperature the Fermi energy. At zero temperature, the expectation value of the particle number is exactly 1 when the energy is less than the Fermi energy, or chemical potential. And it's exactly 0 when the energy is above the Fermi energy. So the orbital is occupied with certainty when the energy is below the Fermi energy, and completely unoccupied when the energy is above the Fermi energy. So there are a bunch of orbitals. Here are their energies. And here's the chemical potential, the Fermi energy. All the orbitals with energy below are filled. And all those above are empty. The total number of particles in the system is capital N. It's the number of orbitals with energy below the Fermi energy. Okay? We're constructing with n particles the lowest possible energy state of the system. Every time we add a particle, we put it in the lowest energy state that's available. We put the first particle in the ground orbital, but then Pauli exclusion principle, we can't put another particle there. We put the next one in the first excited orbital, then the second excited, and so on until we run out of particles. So we have a particle in every orbital up to E Fermi, and the rest are empty. Now, if we introduce a small but non-zero temperature, but which is small compared to the Fermi energy, then this very sharp step gets smoothed out a little bit. Those sharp corners become slightly rounded. So I have a similar picture with, at the Fermi energy now, an occupation number, an expected number of particles in the orbital of 1/2 right at the Fermi energy, then quickly approaching 1 at lower energies, quickly approaching zero at higher energies. A slightly rounded step like that. Yep.
Well, what if your number of particles n is less than the number of orbitals is below zero?
Well, if I want to have some specified number of particles in the system, I will have to choose the chemical potential appropriately.
Okay.
Number of particles depends on the chemical potential. So if you tell me you want n particles at a given temperature, I'll tell you what the chemical potential has to be. If it's zero temperature, that means I have to choose the chemical potential to be in between the nth orbital and the n plus first. Okay? I mean, you can imagine that there's some reservoir connected to the system which can give up particles, and it will, every time it gives up a particle that reduces its energy by mu, okay, because the reservoir has chemical potential mu, and so now we want to construct the most probable configuration. It'll want to keep adding particles until the cost of adding another particle is more than the chemical potential of the reservoir. So given that property of the reservoir, we'll find the configuration with the lowest n orbitals occupied. Now, if it were bosons, on the other hand, at zero temperature, what's going to happen? So again, I've got some set of orbitals. And I want to find the lowest possible energy configuration at zero temperature. I try to minimize the energy. They're altogether n particles. So where do the particles go? Put the first one here. Where's the next one go? There's no reason not to keep putting them in the same orbital, right? This is the ground orbital. There's no Pauli exclusion principle. I just put them all in the lowest orbital. That's the lowest energy state. So n particles all in ground orbital. That was simple. And the distribution function looks like that. Okay. Now, when the temperature is not zero but small, we'll be saying in more detail later exactly what I mean by small. Then there will be a few particles in excited orbitals because we can have more entropy that way. And the distribution function will have that big spike, but then there will be a little bit of a tail. And the chemical potential, we'll see, will be very close to the energy of the ground state orbital. And we'll calculate exactly how the chemical potential has to behave as we increase the number of particles later on. But for now, the basic observation is just that we want to construct the lowest energy configuration at zero temperature. We put all the particles in the lowest orbital, heat up the system a little bit. Well, then there will be a few in excited orbitals, but most of them still in the ground orbital. Okay? Okay, so let's look back at the Fermi-Dirac case. I want to actually apply for now, the Fermi-Dirac distribution to a particular physical situation. I have in mind electrons and metals. But at first we'll just do mathematics that would apply to any Fermi gas. Well, let's remember how to count states. I don't have to remind you about that again. If I consider a box, let's say a cubic box in 3 dimensions with side L, then if I want to sum over all the orbitals, I have to sum over an nx, an ny, and nz. But in the case of a large volume, I can replace that sum by an integral. It becomes actually L over 2 pi cubed times an integral over the wave numbers of the modes, d cubed k if we're in 3 dimensions. And of course, L cubed is just the volume. So if you like, I can say that the number of additional orbitals I get when I change k a little bit is given by volume divided by 2 pi cubed times the volume element in k space. Now let's first of all consider the so-called degenerate case. Degenerate case means 0 temperature. This is called a degenerate Fermi gas. Sorry, the word degenerate has a different meaning than the last time I said the word degenerate. Because before we used degeneracy to talk about the number of different states of a system that have the same energy. Here, degenerate just means the limiting case, the case of 0 temperature where this step is sharp. And similarly, I would call this, the 0 temperature case, the degenerate Bose gas. It's the 0 temperature case. The limiting case in which the temperature goes to 0 and everybody falls into the lowest orbital. So in the degenerate case, for fermions, what's the total number of electrons? Well, what I want to do is I'd like to figure out what the chemical potential has to be, or what the Fermi energy is, so that I get exactly n particles below the Fermi energy. Okay? So I will express this as a sum over orbitals, integrating only over the filled orbitals. So that'll be up to some maximum value of the wave number. And then for higher values of the wave number, the orbitals will be empty. So first of all, there's a factor of 2, because I'm going to consider the case where there's spin. So if I'm counting orbitals, and I guess I lied a little bit here, when I integrate over a wave number, there's an additional factor, which is a spin factor. Now, in the case of electrons, which are spin 1/2, they can be spin up or spin down. So there are 2 possible states for each value of the wave number of an orbital, right? Spin up and spin down. That's what this factor of 2 is. 2 for spin. And then I sum over all the wave numbers of the orbitals. And for that, we get the factor volume divided by 2 pi cubed. And then I'll integrate up to the maximum wave number of filled orbitals. I'll call that the Fermi wave number, k sub f. And then I'm integrating with the 3-dimensional volume element. Kf means the length of the 3-vector k. So I'm integrating over a sphere which has radius 4 pi k squared. Integrate the radius from 0 to kf. Kf equals Fermi wave number equals the maximum k for filled orbitals. At zero temperature. So this allows me to relate the number of particles in the degenerate gas to the Fermi wave number, since we've seen that the total number of particles, n, I have 2 times 4 in the numerator and 2 cubed in the denominator, pi cubed here, pi in the numerator. So it's actually a volume divided by pi squared, and then an integral up to kf dk k squared. And that integral is 1/3 Fermi wave number cubed. So I can write Fermi wave number cubed as 3 pi squared times the number of particles per unit volume. 3 pi squared times the concentration of particles. Okay? And if you think about it, that kind of makes sense, because what we're saying is that the Fermi wavelength, 2 pi over kf, now worrying about numerical factors of order 1, goes like the concentration to the minus 1/3, which is the typical separation between particles in the gas. So you could call that the interparticle spacing. So the maximum in the degenerate gas, remember they're fermions, they don't want to sit on top of one another. In the degenerate gas, the maximum wave number is comparable to the distance between minimum wavelength, 2 pi over kf, is comparable to the distance between particles. They're kind of packed in as close as they can be. Now, these are going to be non-relativistic particles. What I've said here actually would apply, I guess, even if they weren't. But now we'll put in their dispersion relation. That is, they're non-relativistic. And, of course, it's an ideal gas, so no interactions among the particles. All they got is kinetic energy. The kinetic energy is p squared over 2m. Or, in terms of the wave number, h bar k squared over 2m. So that means I can relate the Fermi wave number to the Fermi energy. The energy of the orbital, which is the highest energy orbital that's filled, EF, Fermi energy, is h bar squared over 2m Fermi wave number squared, because that's the relationship between wave number and energy. So it's h bar squared over 2m. And since we've just seen what the Fermi wave number is, it's 3 pi squared n to the 1/3 squared, or in other words, 3 pi squared n to the 2/3. Okay? We can also compute the total energy of the degenerate gas. That's the, I'll call it the ground state energy. For n particles. So that is the spin factor, the volume divided by 2 pi cubed from counting orbitals. Then I integrate 0 up to kf, dk, 4 pi k squared. That's what we had when we were counting orbitals. And now I put in the energy of the orbital, h bar squared over 2m k squared. Okay. So the 8 in the numerator and denominator cancel. As before, I've got, again, pi squared in the denominator, so it's volume over pi squared. There's an extra h bar squared over 2m. And then I've got to integrate up to kf dk, k to the 4th. A k squared from the density of orbitals, a k squared from the energy. That integral is 1/5 k Fermi to the 5th power. I like writing kf to the 5th power as kf cubed times kf squared, don't you? So I got my v over pi squared and a 1/5. Kf cubed, we have seen, I can write as 3 pi squared times concentration. And then the extra kf squared, which I'll combine together with the h squared over 2m, is h bar squared over 2m times kf squared. Well, that's the same thing as the Fermi energy, the chemical potential of the gas. So, volumes cancel out, numerator and denominator. Pi squareds cancel out. I've got a 3/5. So this is just 3/5 number of particles times Fermi energy. So in other words, we've got a sharp distribution function going up to EF. And if this is, well, that was supposed to be 3/5 EF, that's the average energy per particle in the gas, is 3/5 EF. And, well, of course, that depended on various things, like the fact that we were talking about non-relativistic particles, so the energy goes like k squared. Also that we're talking about 3 dimensions, so that the integral over states goes like dk k squared. Anyway, with 3 dimensions, non-relativistic particles, that's what we get. Now, when we compute various properties of the system, the name of the game is we sum up the contribution to the quantity we're interested in coming from each one of the orbitals. Okay? So if there's some property, let's call it x. We want to know the expectation value of the total x. It comes from summing up the value of x in each one of the questions. Oh, okay. Yeah, good question. This 3/5, in order to derive it, we needed two things. Non-relativistic particles, so that energy is proportional to k squared, or p squared, and 3 dimensions. So, dn goes like k squared dk. So if we were in 2 dimensions, say, or if we considered relativistic particles for which the energy goes like p instead of p squared, we would have gotten a different answer. Oh, look, another blackboard. Glad you pointed that out. So if I'm looking at the total value of x, we've learned how to compute the expectation value of a quantity orbital by orbital, and we just sum up contributions from all the orbitals. So I sum over orbitals. I have a distribution function which tells me the expected value of the number of particles in an orbital which has energy E at the specified temperature and chemical potential, and then whatever the value of x is in the orbital. And I sum them all up. So, since we can replace sums over orbitals by integrals, I've been writing it as an integral decay, which was convenient to do. Question?
Sorry, what's x?
Oh, it's just some quantity. For example, e.g., energy, which is the example I've just done, right? We computed the value of the energy by summing over the orbitals. That was this stuff, including the integral 4 pi k squared, and then the energy in that orbital. So whatever it is, that's how we do it. We find out its value in each orbital and sum up the contributions from all the orbitals. Okay. And, well, it's often convenient to write this not as a k integral, but an energy integral. So let's do that. There's some density of orbitals per unit of energy. I'm going to call that script d of E. And then there's the occupation number, and then the value of x for an orbital which has energy E. So sum over orbitals I've just written this way. Or in other words, this is density of orbitals per unit of energy. That is, in the interval between energy E and energy E plus dE, there are d of E and dE orbitals. So it's really a density of orbitals question.
I'm sorry, do we have sum to 1?
The F's don't have to sum to 1.
So then are you just divided by the sum of the probabilities?
Well, you see, I'm talking about the total, right? So I'm adding, so that's what I did with the energy. It's true that I could talk about a probability distribution for the number of particles per orbital. I'm not doing that. For each value of the chemical potential and temperature, there's some expected number of, well, for the value of the energy, say, and the way I find that is well, all right. So in this case, of course, I was doing it for, okay, what did I do here? The same thing I was doing here, but for the degenerate case where F was equal to 1 up to some maximum value kF and 0 thereafter. Okay, but if I wanted to find the energy, for example, at a non-zero temperature, for which F is rounded out, I could do it the same way, but now I would weight the contribution to the energy for each orbital by the expected number of particles in that orbital. Okay? So, of course, because they're fermions, each orbital, there are only two possibilities. It's either empty or it's occupied. So F, you can relate that to the probability of being occupied. But I'm mean by F the expected value for the number of particles. So the expected value for the energy is the expected value for the number of particles times the energy of the orbital. Okay. And same thing for any other quantity you wanted to compute, orbital by orbital. Okay. So this is really the density of orbitals. Everybody calls it the density of states, though, so you should call it that, too. It's a little bit confusing. It's really the density of orbitals, but we'll call it, well, I don't know, maybe I'll call it density of orbitals, but you should call it density of states, because everyone does. Okay, so now let's do a little algebra, because we want to take what I did before, which was to count states by integrating over a wave number and just change that to an integral over energy. It's just a change of variables, but I guess I'll do it because it's kind of important. So remember when we summed over orbitals, we were summing over wave numbers, and then we replaced that by volume over 2 pi cubed and integral 4 pi k squared dk. Or if you want to cancel the factors in numerator and denominator, I can write it as 1 over 2 pi squared times volume integral dk k squared. And now I'd like to convert that to an integral over energy. The relationship between energy and wave number is energy equals h bar squared k squared over 2m. So in the k squared here, I can just replace by, if I want to write it in terms of energy, 2m over h bar squared times the energy. And then I can, since I can write k squared as 2, well, I just did, okay. So if I differentiate both sides, 2k dk is equal to 2m over h bar squared times dE, where E is the energy. And then if I divide by 2k, it means I can write dk as d energy, and then there's a factor of 2m over h bar squared, which is this factor, but then I also have to divide by k and also by 2. So k is just the square root of this. So I'll write the dividing by 2 explicitly. That's the 1/2 comes from this factor of 2. And then for k, I guess I got that wrong, didn't I? No. I guess I have it wrong here. Oh, I see. I want to divide by it. That's the problem. So I can write it as h bar squared over 2me to the 1/2. Okay, so that means for the decay part, I can write it as 1/2 2m over, I see, I wrote a, boy, this is all messed up. What did I do here? I see, I put in a 2 pi when I meant a 2m, right? Okay. Okay, so I have a 2m over h bar squared, but then I also have that to the minus 1/2, so I can combine those together to get 2 pi. There, I said it again, 2m over h bar squared to the 1/2, and then I have an energy to the minus 1/2 dE. But then that's the decay, and then I also, in my expression for summing over states, I have a dk and a k squared, and the k squared is 2m over h bar squared. So that means I can write the sum over all the orbitals. And I guess I want to put the spin factor in too. Did I already do that? I guess that's going to cancel the 1/2. I'll put in the spin factor later. So I'm going to write the sum over the values of the wave number as an integral v over 2 pi squared, because I had a v over 2 pi squared in front of the integral. Then I have altogether 3 factors of square root of 2m over h bar squared, because I had 2m over h bar squared here, and then another 2m over h bar squared to the 1/2 there. I have this 1/2, and then I have epsilon to the 1/2 d epsilon. E to the minus 1/2 became e to the 1/2 because of this extra factor of e. So I can write this as an integral over energy. Well, I don't want to write this, but the sum over orbitals, which might include a spin factor, as an integral over energy, density of orbitals per unit energy, and the density of orbitals is v over 4 pi squared, because I combine the v over 2 pi squared with this 1/2, the 2m over h bar squared to the 3/2, and energy to the 1/2, and then times a possible factor for spin. And in the case of electrons, that would be 2. I guess that looks right. So this is the density of states, or orbitals, including the spin factor. Question?
So on this board, right here, when you're doing the sum,
Mm-hmm.
tau and mu are fixed characteristics of the system, right?
Correct.
And you're so.
But this depends.
On the orbital.
Right.
Okay.
E of orbital.
Cool. Thank you.
Yeah. Thanks. Right. So I'd like to consider a metal. It's a conductor. It's got electrons, which are free to propagate inside the metal. Something like 1 electron per atom in the crystal. And somewhat dubiously, but actually getting results that are reasonable, as we'll see, I'm going to treat the electrons as an ideal gas. And what's the Fermi energy for electrons in a metal? In order of magnitude, any guesses? Say in electron volts? Well, let's look at it this way. We know that the interatomic spacing in a metal is roughly what? Yeah, it's like a Bohr radius, right? It's like an angstrom, something like that. All atoms are about the same size. Right? And so furthermore, we know the Fermi energy, the Fermi wave number is such that the Fermi wavelength is comparable to the interatomic spacing, something like a Bohr radius. What's the kinetic energy for an electron that's confined to roughly a Bohr radius? What's the binding energy of hydrogen? Yeah, it's Rydberg. It's 13.6 eV. So if you have a particle whose wave number is comparable to 2 pi over the Bohr radius, the kinetic energy is going to be of the order of electron volts, right? So for a typical metal, the Fermi energy is actually a few electron volts. What's room temperature in electron volts? Right, so temperature 300 degrees K is about 1/40th of an electron volt. So are electrons in metal at room temperature nearly degenerate? Well, kind of, yeah. I mean, the temperature is small compared to the Fermi energy. So the picture that I drew earlier is going to apply pretty well. And then we have a nearly degenerate situation. This is the Fermi energy, which is electron volts. This is the temperature, which is about 1/40th of an electron volt. And so most of the orbitals down here are foiled, most of them are empty. And all the action is occurring within an energy range near the Fermi level that has a width comparable to the temperature, like 1/40th of an electron volt. Okay? So I would like to understand the heat capacity of this gas. What is the heat capacity of a nearly degenerate Fermi gas? So the heat capacity, that tells us the relationship between a change in the temperature and a change in the internal energy, right? So by heat capacity, I mean change in internal energy per unit of change in temperature. I guess I said this before, but if you look at this function as if you subtract 1/2 from it, so then it becomes antisymmetric about the origin and the Fermi energy. In other words, you can write the distribution function as 1/2 minus 1/2 hyperbolic tangent of x over 2, where x is E minus chemical potential divided by tau. And when we are at low temperature, we can consider the density of states in the region where the occupation number isn't strictly 1 or 0 to be essentially a constant, because it's just a very narrow band in energy where some of the orbitals have occupation number a little less than 1 and some of them a little greater than 0. Okay? So we can suppose density of states is equal to the density of states at the Fermi level, a constant. Oh, wait a minute. Oh, yeah, here we go. Okay, so what I would like to do is I'd like to expand C in powers of the temperature when the temperature is low. the nearly degenerate case. And I'm only going to try to compute the linear term. I'd like to know what its coefficient is, the term that's linear in temperature. So, as I've suggested, the density of states, if we were to expand it about the Fermi energy, would be its value at the Fermi energy plus some term which is linear. If we expand it in a power series in the deviation from the Fermi energy. But for our calculation, which is just to find the linear term, we won't need this term. So we'll be able to just ignore it in our approximation. Yeah.
The density of the Fermi energy is 1/2, right?
Oh, sorry. Density is not the same. It has nothing to do with occupation number. It has to do with how many orbitals there are per unit of energy. So what I meant by D of E is this density of orbitals per unit energy, which actually goes like energy to the 1/2. It's not independent of energy, but on the other hand, we're looking at just a narrow range of energy for which the e to the 1/2 doesn't change much. I can expand e to the 1/2 about EF, and in principle I can include higher order terms, but we're going to, in the leading approximation we'll be making, we won't need those higher order terms. Okay. Of course, we're keeping n fixed as we turn on the temperature, and that means that in this leading approximation, we don't have to change the chemical potential. Now, normally when you change the temperature and you keep the number of particles fixed, you have to adjust the chemical potential to keep the number of particles at a fixed value. But here, we'll be able to assume that the chemical potential up to this linear expansion in temperature is equal to its zero temperature value, the Fermi energy. And the reason is that if we're ignoring the way the density of orbitals varies in this little band, in this distribution function, because of its nice symmetry, because the tang is an odd function, there are just as many vacated orbitals up here as there are filled orbitals down here. Okay? Here, let me say that a little bit more explicitly. So 0 is equal to dn d tau because we're keeping the number of particles fixed. Let's consider how the number varies as we change the temperature a little bit, expanding around 0 temperature. So that's supposed to be 0. I can write it as the derivative with respect to temperature of the density of orbitals d of E times the distribution function. And the temperature dependence is only in the distribution function. So if I, in my leading approximation, I just pull out the density of orbitals at the Fermi level, we got the answer. Cool. Actually, I'd like to write the answer in a slightly different way. Remember the number of particles for the Fermi energy, that is the number of particles up to that energy. I can write that as the integral up to the Fermi energy of the density of orbitals. So we know, since density of orbitals goes like e to the 1/2, its integral is going to go like some number times e to the 3/2. So this is going to be some number times Fermi energy in 3/2. Notice that the density, using the fundamental theorem of calculus or something like that, this is the derivative with respect to the energy at Fermi energy, the number of particles, because the number of particles is the integral of d. D is the derivative of n. But now we see that since this goes like e to the 3/2, its derivative is 3/2 n over the Fermi energy. So I can write this in terms of the total number of particles by replacing the density of orbitals at the Fermi level by 3/2 n over EF. That means that heat capacity, which we just saw was pi squared over 3, tau density of orbitals at the Fermi level, I guess I could say plus order tau squared, which we're ignoring, can also be written in the same approximation as pi squared over 2 because of the 3/2. And then temperature divided by Fermi energy times total number of particles. So, of course, heat capacity scales like system size. It's in sense of quantity. It scales like the number of particles. Its coefficient is dimensionless. Units we're using, energy and temperature, have the same units, and that dimensionless coefficient is essentially temperature divided by Fermi energy, but with some number in front that we computed. All the work was to compute that number.
Sorry, Professor.
Yeah.
I'm a little confused as to what we were doing before when we calculated C. So that integral without the dd tau should give us u, right?
The integral without the dd tau would give us u. Let's see why. We're summing over all orbitals.
Right.
But remember, I originally wrote it this way, and then I said I could treat it as a constant, weighted by the number of orbitals and the energy of the orbital times the occupation.
Okay. Yeah. Okay. Great.
So we're summing up the expected value of the energy for each orbital summed over orbitals.
Yeah. Okay. Thank you.
Now I'm going to do this crazy thing, applying this to electrons and metals. Why is it crazy? Are electrons and metals an ideal gas? Do they interact? How do they interact? So in lots of ways. They've got charges. There's Coulomb interactions between the electrons. They're moving through a lattice. There are all these ions. The atoms ionize to give up the electrons that are flowing around, and they keep bumping into the ions. Not a very ideal gas. But there's this amazing thing, and which is very subtle, and which you're not going to hear explained to you in this course, which is that when you sum up the effects of all these complicated interactions that are going on, what they do is what we call, but this is just words, is dress the electron and this changes the properties of the electrons. As you know, when we're trying to sound sophisticated, this is the word renormalize. This renormalizes properties of the electron, like its mass. What does that mean? It means when the electron is moving along, there's a contribution to its inertia coming from its interaction with other electrons. It's kind of dragging through this system, and it's pulling some of the other electrons, and it's pulling some of the lattice excitations, and all this winds up renormalizing its mass, so it's not the same thing as the mass of an electron in the vacuum. But after you do all this renormalizing and dressing and so on, after that, most of the Coulomb interaction gets used up in dressing the electrons, and the dressed electrons behave like weakly interacting particles. It's kind of a miracle. But it really works. We call this a Landau Fermi liquid theory. Well, the liquid means it's not exactly an ideal gas. There are some interactions. But the electrons, after they get all dressed up, behave more or less like weakly interacting particles. So the dressed electrons have weak interactions, and so it's a nearly ideal gas. And we can try to take into account the interactions with some kind of systematic perturbation expansion. That's a very complicated story, which I'm not going to try to explain. So we're just treating it like an ideal gas. Like, suppose it's an alkali metal. Alkali metals are simple because they have one valence electron, which they give up. So there's about one electron per atom, contributing to the electrical conductivity of the system. So the concentration of electrons is about the concentration of atoms. So you can calculate the concentration of atoms. You know the density of the material. You know the atomic weight of the atom in question. Let's say it's potassium. Just a calculation heavily you can do. Okay, that doesn't mean Kelvin. That means potassium has a density of about 1.3 times 10 to the 22 atoms per cubic centimeter. So we'll take that to be the density of electrons, the concentration of electrons in our ideal gas. That means we know how to compute its Fermi energy. Formula for that down before. It's h bar squared over 2m, where now m is the mass of the electron, 3 I squared concentration, which is that number, at the 2/3. You put in the numbers, and like I said, it's in order of magnitude not that different from Rydberg. It's about 2.1 electron volts, actually. But that's a high temperature. If you put that in degrees K, it's about 24,000 degrees. So, as I asserted earlier, room temperature, which is 300 degrees, is much smaller. This is highly degenerate. So our calculation should apply. And we computed the coefficient of the linear term in the heat capacity. So for the heat capacity, we get some number, which we figured out. That's the temperature plus higher order in temperature. Well, there's something else that we've already talked about, a contribution to the heat capacity in solids. Does anybody remember what that was? Wasn't that long ago. What else did I tell you about heat capacities of solids? If this guy Debye, what did he do? Remember we learned about this Debye T cubed law. And so there's also a contribution, which is much bigger than the high order contribution, actually reasonable temperatures coming from high order in tau in our computation of the electron heat capacity. This comes from the lattice vibrations. This is from electrons. This, remember, is lattice vibrations. And we know what A is because we computed it in Debye theory. I'm sure you remember. It's 12 pi to the 4th divided by 5, the number of atoms in the crystal, Debye temperature to the minus 3. That's coming from all of that gas of phonons that Debye studied. Gamma, we just worked out what that is. Gamma is I squared over 2, number divided by
EF. So one of these guys is going like linearly with temperature, the other one turns on more slowly. So this is the electron contribution to heat capacity as a function of temperature. This is the Debye contribution. Eventually they cross. The Debye contribution has its domain in which is the dominant term, and when I said it worked experimentally, we were talking about that in temperature. So you can work out, I guess I'm not going to do it explicitly on the board, about where that crossover occurs. Does anybody remember what the Debye temperature is, roughly, in a typical solid? I mean, is it like a degree or 10,000 degrees? Anybody remember? I'll talk to you about that.
So it's about 100.
Yeah, about 100. And in fact, when you work it out for potassium, theta is 91 degrees K. And you can also work out the crossover, where these two terms are comparable. I'll just tell you the answer. Is when temperature divided by Debye temperature squared is 5 over 24 pi squared. Debye temperature divided by Fermi energy. I just equated these two to see roughly where they cross over. And it's kind of interesting to see that keeping those numbers was worthwhile, because 5 over 24 pi squared is a pretty small number. And so where the crossover occurs is actually when the temperature over the Debye temperature is about 1%. Because the Debye temperature is something like 1% of Fermi energy. And then this number is something like 1 over 50. And so this is something like 10 to the minus 4. And the crossover actually occurs at about 1 degree K. So if you want to see this linear term, you've got to go down to low enough temperature so you don't get fooled by the phonons. Phonons freeze out faster. You can see the electrons at low temperature. And this linear law works quite well. The value of gamma that we computed isn't exactly right. For potassium, it's off by about 20%. It's actually pretty good when you consider what a naive approximation this is. Treating the gas as an ideal gas with the mass equal to the mass of a free potassium atom. So qualitatively, it's the right picture. We can think of the electrons as an ideal gas. It's nearly degenerate. It has a contribution to its heat capacity that's linear in temperature and low temperature, and you can estimate